Pick up a rock. Any rock. Hold it in your hand. Feel the weight of it. Now let me ask you something so simple it sounds stupid. What is that rock? I mean, really, what is it? You'd say, well, it's a rock. It's a solid object. It has a shape, a weight, a color. If I throw it, it follows a nice arc through the air and lands somewhere predictable. End of story. Right? Wrong. That rock is a lie. Or rather, the rock is real. But what you think it is, that's the lie. Because that rock exists simultaneously on at least 7 different layers of reality, and most of the time even trained physicists only work on 3 of them. The other 4 are sitting right there holding everything together, and almost nobody talks about them in a single conversation. I've spent my career peeling things apart, finding out what's underneath. And what I've noticed is that every time you peel away one layer, the next one doesn't look anything like the one before it. The rules change. The vocabulary changes. The very meaning of what exists changes. It's as if the universe is a building where each floor was designed by a different architect who never spoke to the others, and yet somehow the whole structure stands. So that's what we're going to do. We're going to take that rock, this boring little rock, and we're going to peel it open layer by layer until you see something you won't be able to unsee. Let's start where everybody starts. The first layer. I call it the ordinary. You throw the rock, it goes up, it comes back down. You put it on a table, it stays there. You push it, it slides. If you push it harder, it slides faster. This is the world Isaac Newton handed us over 300 years ago. Forces, masses, accelerations. Every object moves in a way that you can predict if you know the forces acting on it. A planet in orbit, a bullet fired from a gun, a rock tossed across a field. Same rules, same layer, and those rules are spectacularly good. Think about what Newton gave us. You stand on a hill and throw that rock at an angle, and I can tell you before it leaves your hand exactly where it will land. I can tell you how high it will go. I can tell you how long it will be in the air. All I need is the angle, the speed, and the acceleration due to gravity. 3 numbers, and the entire trajectory unfolds like a film I've already watched. That's not just convenient, that's a revelation. Before Newton, motion was a mystery. Why do things fall? Why does the moon not fall? Aristotle had answers, but they were wrong. He thought heavy things fall faster. He thought the celestial realm operated under different laws than the earthly one. Newton swept all of that away in one stroke. He said there is one law of gravity, and it works everywhere. The same force that pulls the apple from the tree holds the moon in orbit. The same equation, the same constant. Universal gravitation. We sent people to the moon with this layer. We built bridges and skyscrapers and jet engines. We calculated the orbits of comets decades before they appeared in the sky. You can do an enormous amount with just the ordinary, and for about 200 years that was physics. Measure the positions, measure the velocities, write down the forces, calculate the future. Done. Deterministic, clockwork, a universe that runs like a machine, and once you know the starting conditions, you know everything that will ever happen. There was a fellow named Pierre-Simon Laplace who took this idea to its logical conclusion. He imagined a demon, a hypothetical being who knew the position and velocity of every particle in the universe at one instant. Laplace said that demon could calculate the entire future and the entire past. Nothing hidden, nothing uncertain, everything determined from the very beginning. Feels complete, doesn't it? It's not even close, because already, sitting inside that rock, there is a second layer screaming at you, and Newton couldn't hear it. Put your hand on the rock. Is it warm? Is it cool? Is it cool? Is it that warmth or that coolness? That's the second layer showing itself. I call this one the hidden crowd. See, what you feel as temperature isn't a force. It isn't a thing you can point at. You can't find heat if you zoom in close enough. What you find instead is motion. Random, chaotic, furious motion of things so small you can't see them. Every atom in that rock is jiggling, vibrating, bouncing around in its little cage of neighboring atoms. Trillions upon trillions of them, all doing their own private little dance. And what you feel as warmth is the collective effect of all that hidden activity. This is statistical mechanics, and it's one of the deepest ideas in all of science. It says that when you have enormous numbers of particles, new laws emerge. Laws that don't exist at the level of individual objects. You cannot define the temperature of one atom. The concept doesn't even make sense. Temperature is a property of crowds. It's like asking what the traffic pattern is of a single car. The word has no meaning until there are thousands of cars interacting on a highway. Ludwig Boltzmann figured this out in the 1870s, and it nearly destroyed him. The scientific establishment of his time didn't believe in atoms. Many prominent physicists thought atoms were a convenient fiction, a calculating trick. Boltzmann said, no, atoms are real, and the laws of thermodynamics, the laws of heat and energy and entropy, emerge from the collective behavior of unimaginably vast numbers of them. He was right, but the resistance was so fierce and the attack so personal that Boltzmann suffered terribly. He took his own life in 1906, just a few years before experiments confirmed atoms beyond any doubt, one of the great tragedies of science. But what Boltzmann gave us was a key to a door nobody knew existed. He showed that entropy, the thing that measures disorder, has a precise statistical meaning. The entropy of a system is proportional to the logarithm of the number of ways you can rearrange its microscopic parts without changing what it looks like, macroscopically. A gas with all its molecules in one corner of the room has low entropy because there's basically only one arrangement that puts them all in that corner. A gas with molecules spread evenly throughout the room has high entropy because there are astronomically more ways to arrange them evenly than to pile them in a corner. But nobody expected what comes next. From this crowd behavior, you get a brand new law that has no equivalent in Newton's mechanics. You get the second law of thermodynamics. Things move from order to disorder. Hot objects cool down. Cold objects don't spontaneously heat up. You can stir cream into coffee, but you can never unstir it. Time at this layer has a direction, and that direction comes purely from probability, from the overwhelming statistical likelihood that a vast crowd of particles will move toward the most probable arrangement. Think about that for a second. There's no force pushing things toward disorder. There's no law that says thou shalt increase entropy. It's just math. It's just counting. There are more ways to be disordered than ordered, so random motion will overwhelmingly take you toward disorder. Not because it must, but because it's almost certain. The probability that every molecule of air in this room will spontaneously drift to one corner is not zero. It's just so astronomically small that if you waited for it from the beginning of the universe until now, and then waited that long again, a trillion times, it still wouldn't happen. Newton's layer doesn't have a direction of time. Run Newton's equations backwards and everything still makes perfect sense. Balls unfall, planets unorbit, but at the layer of the hidden crowd, time only goes one way. Something fundamental has changed, and all we did was count. So already we have two layers, the ordinary and the hidden crowd, and they contradict each other in a deep way. One is reversible, the other is not. One deals with objects, the other deals with statistics. And if you're an engineer or a chemist or someone doing everyday physics, these two layers and maybe one more are all you ever need. But nature is not done with us, not remotely. Let me take that rock and do something simple. Put it in the dark. Now shine a light on it. You see the rock? You see its color, its texture, its shape. Fine. But stop for a moment and ask yourself what just happened. Light left the source, traveled through empty space, bounced off the rock, entered your eye, and your brain assembled an image. That process, that interaction between light and matter, that's the third layer. I call it the invisible web. Before the middle of the 19th century, electricity and magnetism were two separate subjects. You had sparks and shocks over here, and you had magnets and compasses over there. Then along comes James Clerk Maxwell, and he writes down 4 equations. 4. And those 4 equations reveal that electricity and magnetism are the same thing. They are two aspects of a single entity, the electromagnetic field. And this field doesn't just connect wires and magnets. It fills all of space. It's between you and the wall right now. It's between the Earth and the Sun. Every point in the universe has an electromagnetic field value. And when that field ripples, the ripple travels at the speed of light, because the ripple is light. That's worth pausing on. Light is not a substance. Light is a disturbance in the electromagnetic field. That it's a wave that carries itself. The electric part generates the magnetic part, and the magnetic part generates the electric part, and this self-sustaining oscillation propagates forward at 186,000 miles per second forever until something gets in the way. Maxwell didn't know he was about to have one of the greatest moments in the history of science. But When he wrote down his equations and calculated the speed of these electromagnetic waves, the number he got was the speed of light. Exactly. He didn't put light into his equations, he put in electricity and magnetism. And light fell out. That's the kind of moment that makes you stand up from your desk and pace around the room. He had unified three things that seemed completely unrelated, electricity, magnetism, and optics, into one framework with four equations. It's one of the greatest achievements of the human mind. But Maxwell's layer introduced something that didn't exist in the first two. A field. Not an object. Not a particle. A thing that exists everywhere, that has a value at every point, that changes and flows and interacts with charged matter. Newton dealt in forces between objects, like invisible ropes pulling things together across empty space. He wasn't happy about it, by the way. He called it action at a distance and said it was philosophically absurd, but the math worked, so he used it. Maxwell said, no, there's something filling the space between the objects, and the objects push and pull on that, and that pushes and pulls on other objects. The field is the intermediary. The field is real. This idea, the idea that fields are physically real things, not just mathematical conveniences, was revolutionary. Because up until Maxwell, physics was about stuff, particles, objects, things you could point at. Now there was this invisible entity permeating all of space, carrying energy, carrying momentum, carrying information from one charged particle to another at a finite speed. That finite speed part is crucial. In Newton's world, if you move the sun, the earth feels it instantly. In Maxwell's world, there's a delay. The newt has to travel through the field, and it travels at the speed of light. That delay, that finite propagation, would later become the cornerstone of Einstein's special relativity. And this is where most people stop. If you take an undergraduate physics degree, by the time you've covered mechanics, thermodynamics, and electromagnetism, you've got a solid toolkit. You can explain most of what you encounter in daily life. Rocks fall, things heat up, light bounces around. 3 layers, very satisfying. But you've missed the basement, and the sub-basement, and the thing underneath the sub-basement, and maybe something underneath that. Let's go down. Layer 4. The uncertain fabric. Zoom in on the atoms inside that rock. Zoom in far enough, and something absolutely bizarre starts to happen. The rules change. Not a little bit, completely. At the scale of atoms and smaller, the universe doesn't behave like tiny billiard balls bouncing around. It behaves like nothing you've ever experienced. An electron in that rock doesn't have a definite position. No, I don't mean we can't measure it precisely enough. I mean, it genuinely does not have one. Until you look, the electron exists as a kind of blur of possibilities, a wave of probabilities spread out over space. The atom has no hard edges. The electron is not orbiting the nucleus the way a planet orbits a star. It's smeared out in a cloud, and the cloud is densest where the electron is most likely to be found, but it's everywhere in that cloud simultaneously. This is quantum mechanics, and when I say it changed everything, I mean it changed the meaning of the word exist. In the ordinary layer, things are somewhere. In the uncertain fabric, things are in many places at once in a very precise mathematical way, described by something called a wave function. The wave function is a recipe for calculating probabilities. Wherever the wave function is large, the particle is likely to be found. Where it's small, the particle probably isn't. But the particle doesn't choose a location until something interacts with it, until a measurement happens. Einstein hated this. He spent the last 30 years of his life fighting it. He said God does not play dice with the universe. And Niels Bohr reportedly told him to stop telling God what to do. The argument was fierce and brilliant, and it went on for decades. And the astonishing result is that Einstein lost. Every experiment we've ever done confirms the quantum picture. Reality at the small scale is genuinely probabilistic. Not because we're ignorant, because that's how it is. But let me show you how deep the uncertain fabric goes, because it's not just about fuzzy positions. There's a thing called quantum tunneling, and it's happening in your rock right now. Imagine a ball rolling toward a hill. If the ball doesn't have enough energy to get over the hill, it stops and rolls back. That's what Newton says. But at the quantum layer, a particle heading toward an energy barrier has a done-go probability of appearing on the other side. Not going over, not going through, just appearing there as if the barrier didn't exist, with some probability that depends on how wide and how tall the barrier is. This isn't a theory waiting for confirmation. This is how the sun works. The protons in the sun's core don't have enough energy to overcome their electrical repulsion and fuse together. Not by classical standards. But they tunnel through the barrier, and when they do, they fuse and they release the energy that lights up the entire solar system. If quantum tunneling didn't exist, the sun wouldn't shine. Stars wouldn't burn. You wouldn't be here. That rock in your hand, the atoms in it were forged inside stars that could only ignite because of this layer. And there's one more thing about the uncertain fabric that I have to tell you, because it's possibly the strangest single feature of the natural world. Entanglement. You can prepare two particles so that their quantum states are linked, not connected by a wire, not communicating, linked in a way that has no classical analogy. You separate them. Put one on this side of the room, the other on the far side, or the other side of the galaxy, it doesn't matter. Now measure a property of the first particle. The instant you do, the second particle's state is determined. Not because a signal traveled between them, not because they agreed ahead of time. The correlation is stronger than any classical scheme could produce. Einstein called it spooky action at a distance, and he used it as an argument that quantum mechanics must be incomplete, that there had to be hidden variables we weren't seeing. In 1964, John Bell proved mathematically that if hidden variables existed, certain experimental measurements would obey a particular inequality. And in the 1980s, experiments by Alain Aspect and others showed that Bell's inequality is violated. Conclusively, the correlations are real, they're non-classical, and they don't depend on hidden information shared in advance. Nature really does this. Two particles separated by any distance sharing a state that isn't fully real until you poke one of them. Nobody fully understands what entanglement means. It's one of the features of quantum mechanics that every interpretation of quantum mechanics has to grapple with, and every interpretation grapples with it differently. But it's real. It's been confirmed thousands of times. And as we'll see when we get to the seventh layer, it may turn out to be the key that unlocks everything. So now we have four: the ordinary, the hidden crowd, the invisible web, and the uncertain fabric. And already the picture is richer than most people ever see. But we're only a little past halfway. Let me show you the layer that most physicists use every day but almost never explain to anyone. Layer 5, the nuclear vault. Now at this point in a lecture, somebody always raises their hand. They say, "Professor Feynman, we've got 4 layers. Mechanics, thermodynamics, electromagnetism, quantum mechanics. That's a lot. Why isn't that the whole story?" And I love that question because the answer is embarrassing. It's embarrassing because if you take those 4 layers and try to explain something basic, something a child would ask, like why is this rock heavy? You can't do it, not really. Mechanics tells you the rock has mass. Thermodynamics tells you the atoms are jiggling. Electromagnetism tells you the electrons are bound to nuclei. Quantum mechanics tells you the electrons exist as probability clouds. Wonderful, but where does the mass actually come from? None of those 4 layers can answer that. For that, you need to go inside the nucleus, and that's a very different country. Take that rock, break it apart, keep breaking. You get grains. Break those, you get molecules. Break those, you get atoms. Now try to break the atom. This is where you run into something ferocious. Because the nucleus of an atom, the tiny dense core where almost all the mass lives, is held together by a force so strong it makes electromagnetism look like a gentle suggestion. This is the strong nuclear force, and it operates on a completely different scale and with completely different rules than anything in the first 4 layers. Let me give you a sense of the scale. The atom is already small, about 1/10 of a nanometer across, which is 1/10 billionth of a meter. But the nucleus is about 100,000 times smaller than the atom. If the atom were the size of a football stadium, the nucleus would be a marble sitting on the 50-yard line. And yet that marble contains over 99.9% of the atom's mass. Everything that gives matter its weight is crammed into that tiny speck. The strong force has a range of about 1 femtometer, which is 1/4,000,000th of a meter. Beyond that distance, it effectively doesn't exist. Inside that distance, it is the most powerful interaction in the known universe. It is what keeps protons and neutrons glued together inside the nucleus, despite the fact that protons are all positively charged and should be flying apart from electrical repulsion. The strong force doesn't care. It grabs those protons and holds them, and it says you're not going anywhere. But it does something even more peculiar. The particles that feel the strong force, the quarks inside protons and neutrons, they carry a type of charge that has no analogy in everyday life. Electrical charge is simple. positive or negative. Two flavors. Quark charge comes in three, and physicists, in a fit of either whimsy or desperation, call them colors. Red, green, blue. Not real colors, obviously, just labels. But the rule is that quarks can only exist in combinations that are color neutral, meaning the colors cancel out. Three quarks, one of each color, make a proton or neutron. A quark and an antiquark with complementary colors make a meson. You never see a lone quark ever. Try to pull one out, and the energy you put in creates new quarks, and they pair up before the original quark gets free. It's like trying to separate two ends of a rubber band by pulling harder. At some point the band snaps, and now you have two rubber bands. You're no closer to isolating one end. This is called confinement, and it's one of the strangest features of the strong force. The particles that carry this force, the gluons, themselves carry color charge, which means gluons interact with each other, not just with quarks. Compare that to electromagnetism. A photon carries the electromagnetic force, but it has no electric charge, so photons pass right through each other, completely indifferent. Gluons don't have that luxury. They grab onto each other, forming tubes of force between quarks, and that self-interaction is what makes the strong force so weird, so powerful, and so short-ranged. It also makes the math incredibly difficult. Electrodynamics is hard enough. Quantum chromodynamics, the theory of the strong force, is a beast that has driven some of the most talented calculators in the world to rely on supercomputers just to extract basic predictions. There's also a weak nuclear force hiding inside that rock. It's quieter than the strong force and far more subtle, but it does something no other force can do. It changes identity. A neutron sitting inside a nucleus can, through the weak force, transform into a proton, spitting out an electron and a ghostly particle called a neutrino in the process. This is radioactive beta decay, and it means the weak force is the only interaction in nature that can actually rearrange what a particle is, not just where it goes or how fast it moves. Every other force pushes or pulls. The weak force transmutes. Most physics education barely dips into this layer. You might learn that the nucleus exists, that it's held together by the strong force, and then you move on. But this layer is where most of the mass in the universe comes from. The quarks themselves are almost massless. What gives a proton its heft is the energy of the strong force field inside it. E equals mc squared, remember. Energy is mass. The frantic, roiling energy of gluons and quark interactions is what makes that rock heavy. Take away the strong force and your rock weighs almost nothing. All right, 5 layers deep, you might think there's nothing left to surprise you. Let me fix that immediately. I call the 6th layer the seething vacuum, and the name alone should tell you something has gone wrong with our intuitions. Take everything out of the rock. Remove all the atoms, all the particles, every scrap of matter and radiation. What's left? Empty space. A vacuum. Nothing. Except it's not nothing. It's wildly, outrageously, spectacularly not nothing. According to quantum field theory, which is the marriage of quantum mechanics and special relativity, what we call empty space is actually a frothing sea of activity. The electromagnetic field is still there. The strong force field is still there. Every field in nature is still there, filling all of space, and they're all in their ground state, their lowest energy state. But the uncertainty principle says that a field can't sit perfectly still. Even in its lowest state, it fluctuates. Tiny random ephemeral fluctuations that blink in and out of existence too fast to observe directly, but their effects are real, measurable, and profound. These are sometimes called virtual particles, though that name is a bit misleading. They're not particles in the way you'd normally think of them. They're fluctuations in the fields, but they have consequences. Here's one. Take 2 flat metal plates and put them very close together in a vacuum with nothing between them. Classical physics says nothing happens, there's nothing there. No matter, no fields, no reason for anything to occur. But in 1948, a Dutch physicist named Hendrik Casimir predicted that those plates would feel a force pushing them together. Not from gravity, not from static electricity, not from magnetism, from the vacuum itself. The reasoning goes like this. The fluctuations between the plates are restricted by the plates, like only certain wavelengths of sound can resonate inside a pipe. Short wavelengths fit, long ones don't. Outside the plates, all wavelengths are allowed. No restrictions. So there's more fluctuation pressure pushing on the plates from outside than from between them, and the plates get pushed together. It's a force generated by the geometry of empty space. This was measured experimentally in 1997 by Steve Lamoro, and Casimir was right. The force is tiny, but it's there, and it matches the prediction. The vacuum is pushing on things. Empty space has structure. It has energy, it has a character. And this isn't philosophy, it's measurable physics. But the seething vacuum creates one of the most embarrassing problems in all of theoretical physics. If you try to calculate how much energy the vacuum should have, using the standard rules of quantum field theory, you get an answer that is absurdly incomprehensibly large. The predicted vacuum energy is roughly 10 to the power of 120 times larger than what we observe. That's not off by a factor of 2, that's not off by a factor of 1,000,000. That's off by a 1 followed by 120 zeros. Some people call it the worst prediction in the history of physics, and they're not exaggerating. Something is very wrong with our understanding of this layer, and nobody knows what. There are ideas, there are speculations, but there's no consensus. The seething vacuum is real. The math describing it works amazingly well for calculating particle interactions, scattering amplitudes, magnetic moments of electrons to 12 decimal places of accuracy. But the vacuum energy calculation is a disaster, and it's been a disaster for decades. This is one of the great unsolved mysteries, and it connects directly to the seventh layer. But I'm not done with the sixth yet. Because the seething vacuum does something else that most people have never heard of. It gives particles their mass. The Higgs field, which was proposed in 1964 and confirmed experimentally in 2012 at the Large Hadron Collider, is a quantum field that fills all of space, like the others. But unlike the electromagnetic field, the Higgs field has a ton-go-hour value even in its ground state. It's not zero everywhere, it's some constant value everywhere. And when certain particles move through this field, they interact with it. And that interaction resists their acceleration, and that resistance is what we experience as mass. Not all mass. Remember, most of the proton's mass comes from the strong force energy inside it. But the mass of the electron, the mass of the quarks themselves, the mass of the W and Z bosons that carry the weak force that comes from the Higgs field, it's as if the whole universe is filled with an invisible molasses, and some particles get stuck in it more than others, and how stuck they are determines how heavy they feel. The photon, by the way, doesn't interact with the Higgs field at all. And that's why it's massless, and that's why it travels at the speed of light. If the Higgs field weren't there, or if it somehow turned off, every particle would be massless. Electrons would fly around at the speed of light. They could never be captured by nuclei. Atoms couldn't form. Chemistry wouldn't exist. Biology wouldn't exist. The entire structure of matter depends on a field that was proposed as an elegant mathematical trick and turned out to be physically real. So empty space isn't empty, it's a medium. It has properties. It interacts with matter. It gives particles mass. It pushes metal plates together. And we don't fully understand its energy budget. That's layer 6, and if it doesn't make you a little dizzy, you're not paying close enough attention. All right, now the 7th. This is the one that keeps me up at night, and I suspect it'll keep you up tonight too. Layer 7. I don't have a cute name for it. Let me just call it what it is. The shape of space-time. In all the previous layers, space and time were the stage. The actors changed, the rules changed, the forces changed. But the stage itself, the flat, quiet, passive background in which everything happens, that stayed the same. Newton assumed it, Maxwell assumed it, even quantum mechanics assumes it. Space is there, time ticks, things happen inside them. Einstein said no, space-time isn't the stage, it's one of the actors. General relativity, which Einstein published in 1915, says that mass and energy don't just sit in space-time. They bend it, they warp it, they shape it. And the warping of space-time is what we experience as gravity. The Earth doesn't pull you down with some invisible rope. The Earth bends the space-time around it, and you, moving forward in time, find that your path through space-time curves toward the Earth. You're not being pulled, you're following the shape of space itself. And this isn't just a reinterpretation. It predicts things Newton couldn't. It predicts that light bends around massive objects, not because light has mass, but because the space it's traveling through is curved. This was confirmed during a solar eclipse in 1919. It predicts that time runs slower in strong gravitational fields. This has been confirmed with atomic clocks on airplanes. Your GPS system has to correct for it, or your position would drift by kilometers every day. It predicts black holes, regions where space-time curves so sharply that nothing, not even light, can escape. It predicts gravitational waves, ripples in the fabric of space-time itself, caused by colliding massive objects. And these were detected directly for the first time in 2015. Two black holes, each about 30 times the mass of the Sun, spiraling into each other a billion light-years away, merging in a cataclysm that for a brief instant released more energy than all the stars in the observable universe combined, and the signal that reached Earth after traveling for over 1 billion years was a stretch of space smaller than 1,000th the diameter of a proton. That's how sensitive the LIGO detectors had to be. And they detected it, space-time rippled, and we felt it. Space-time is dynamic. It breathes, it stretches, it vibrates. It can be torn, as far as we know, into singularities where the curvature becomes infinite and our equations break down. At the center of every black hole, general relativity predicts a point of infinite density, infinite curvature, a place where the math says, I give up. That's not a satisfying answer. That's a confession. The theory is telling us it has reached its limits. And here's where the seventh layer reveals the deepest problem in all of physics. Because this layer and the fourth layer, the uncertain fabric, do not get along. General relativity is a smooth, continuous theory. Space-time is a fabric. You can stretch it, bend it, but it flows. Quantum mechanics is a janky, probabilistic, discrete theory. Things come in chunks, energy is quantized, positions are uncertain. When you try to apply quantum rules to space-time itself, when you try to ask what the fabric of the universe does at the smallest possible scale, the Planck scale, about 10 to the minus 35 meters, the math explodes. You get infinities. You get nonsense. You get predictions that are not just wrong but meaningless. This is the problem of quantum gravity, and it has been unsolved for nearly a century. There are attempts. String theory imagines that at the very bottom, particles are tiny vibrating strings, and different vibration modes produce different particles, like different notes from the same guitar string. Other approaches try to quantize space-time directly, treating space itself as a network of discrete chunks at the Planck scale, pixels of reality itself. These ideas are mathematically beautiful. Some of them may even be right, but none of them have made a prediction we can test with current experiments. Not one. We are stuck. And we have been stuck for decades. And the reason this matters, the reason this isn't just an academic puzzle, is that the seventh layer tells us everything above it is provisional. If we can't describe space-time quantum mechanically, then we don't truly understand what space and time are. And if we don't understand what space and time are, then every layer built on top of them is in some sense a working approximation. Spectacularly useful. But not the final word. Let me just lay them out for you, all 7, so you can see them stacked. At the top, the ordinary Newton's world, forces and motions, objects with definite positions and velocities, a clockwork universe. Below that, the hidden crowd, thermodynamics, the statistical behavior of enormous numbers of particles, giving rise to temperature, entropy, and the arrow of time. Below that, the invisible web, electromagnetism, fields that fill all of space, carrying light, binding atoms into molecules, mediating every chemical reaction and biological process in your body. Below that, the uncertain fabric, quantum mechanics, probability, superposition, entanglement, the dissolution of certainty at the smallest scales. Below that, the nuclear vault, the strong and weak forces, confinement, color charge, the source of nearly all the mass in ordinary matter. Below that, the seething vacuum, quantum field theory, fluctuations in empty space, the Higgs field, virtual particles, the Casimir effect, a vacuum energy problem that embarrasses every theorist alive. And at the very bottom, the shape of space-time, general relativity, a dynamic fabric that bends and ripples and may, at some scale we haven't reached, dissolve into something we don't have a word for yet. 7 layers, all of them present in your rock, all of them active right now. And here's what I find most extraordinary. Each layer was discovered because someone noticed that the layer above it couldn't answer some particular question. Newton couldn't explain heat. Heat couldn't explain light. Light couldn't explain atomic stability. Atomic physics couldn't explain nuclear binding. Nuclear physics couldn't explain why particles have mass. And mass can't explain what space-time is. Every layer exists because the one above it failed to answer a question it couldn't even formulate. And if the pattern holds, and I think it does, the 7th layer will eventually be surpassed by an 8th, maybe a 9th. We just can't see them yet. And look, the pattern isn't just about the layers being incomplete. It's about the nature of the incompleteness. Each time, the missing piece was something the previous framework couldn't even formulate as a question. Newton couldn't ask what is temperature because his framework didn't have the vocabulary for statistical behavior. Maxwell couldn't ask why is the atom stable because his framework predicted that electrons should spiral into the nucleus in a tiny fraction of a second, radiating energy the whole way down. The atom should not exist according to classical electromagnetism, and yet here we are made of atoms, asking the question, that's not a small failure. That's the kind of failure that tells you something about the structure of knowledge itself. I want to say one more thing about this because it's the thing that really gets to me. Most of the time when people talk about physics, they talk about one layer at a time. Classical mechanics in one course, thermodynamics in another, quantum mechanics in a third, and that makes sense for education. You have to learn the pieces before you see the puzzle. But the consequences are that even professionals spend most of their careers working on one or two layers, and they rarely step back to see the whole stack. And the stack is where the beauty is. The stack is where you see that nature isn't a collection of separate rule books. It's one thing, one insanely complicated, deeply interconnected, maddeningly beautiful thing that shows you different faces depending on how closely you look. The rock doesn't care which layer you're examining. All 7 are happening at once. The atoms vibrate thermally while the electrons obey quantum probability clouds, while the nuclei are held together by gluon interactions, while the vacuum fluctuate around them, while the space-time they sit in curves gently under the rock's own mass. All of it simultaneously in a piece of stone you could skip across a pond. And you want to know what I think is going to happen next? I think someone someday is going to find a way to see through all 7 layers at once, and they're going to see something none of us expected. Not a new particle, not a new force, something else, something we don't have the language for yet, a connection between information and geometry, or between entropy and gravity, or between the vacuum and the structure of space-time itself. There are already hints. There's a result from the 1970s from Jacob Bekenstein and Stephen Hawking that says black holes have entropy. Not just a little entropy, enormous entropy, the most entropic objects in the universe per unit volume. And the amount of that entropy is proportional not to the volume of the black hole, but to the area of its event horizon, its boundary. Let that sink in. The amount of information you can store in a region of space is proportional not to the volume of that region, but to the area of its boundary. That's insane. That's like saying the amount of furniture you can fit in a room depends not on how big the room is, but on how much wallpaper you'd need to cover the walls. Volume scales as the cube of the size, area scales as the square. They're different. They shouldn't give you the same answer. But the Bekenstein-Hawking formula says the boundary wins. This is called the holographic principle, and it more than suggests, it practically screams that there's a deep connection between thermodynamics, the 2nd layer, and space-time geometry, the 7th layer, that nobody fully understands. The information about what's inside a volume of space is encoded on its surface, as if 3-dimensional reality were a projection from a 2-dimensional boundary, like a hologram. Some of the sharpest people working today think that space-time itself might emerge from quantum entanglement, that the fabric of the universe isn't fundamental at all, but is woven from quantum information, that the geometry of space is in some precise mathematical sense a map of how entangled the underlying quantum degrees of freedom are. If that's true, then layer 4 and layer 7 are the same layer, seen from different angles. There's even a conjecture proposed by Juan Maldacena and Leonard Susskind, sometimes written as ER equals EPR. ER stands for Einstein-Rosen, as in Einstein-Rosen bridge, which is a wormhole, a tunnel through space-time connecting 2 distant points. EPR stands for Einstein-Podolsky-Rosen, as in the famous thought experiment about entangled particles. The conjecture says that every pair of entangled particles is connected by a tiny wormhole. Entanglement is geometry. Geometry is entanglement. The quantum layer and the space-time layer are 2 descriptions of the same underlying reality. If that's right, think about what it means. When you entangle 2 photons in a lab, you're not just creating a statistical correlation. You're building a microscopic bridge in the structure of space-time. And the space-time you walk around in, the space-time that holds your rock on the table, is itself a web of trillions upon trillions of these entanglement connections, woven together so densely and so coherently that it feels smooth and classical and ordinary. The ordinary layer 1 would then be the zoomed-out view of something fundamentally quantum. The circle closes. Can you imagine? Two layers that seem totally separate, one governing the tiny and probabilistic, the other governing the vast and geometric, turning out to be reflections of each other. That would mean the stack doesn't go down forever. At some point the layers fold back on themselves, and what looked like 7 floors is actually a circle. We don't know if that's right. We don't have the equations yet. But the hints are getting louder. And the people working on this are not cranks. They're the best minds of this generation. And they are closing in on something. So here's what I want to leave you with. That rock in your hand is not a simple thing. It was never a simple thing. Every time in history someone said, I understand this rock, nature said, look closer. And when they looked closer, there was another layer. Every single time for 300 years without exception. Where I see no reason that pattern will stop. There is something beneath the 7th layer. And when we find it, it will make the first 7 look obvious, the way Maxwell made Newton look obvious, the way quantum mechanics made Maxwell look obvious. The deepest lesson from 3 centuries of physics is not any particular law. It's not F equals ma, or E equals mc squared, or the Schrödinger equation. The deepest lesson is humility. Every generation of physicists believed they were close to the final answer. Every generation was wrong. And the wrongness wasn't random. It always pointed in the same direction, toward more layers, more depth, more strangeness, more beauty. The universe is not what it looks like. It never has been. And the only honest reaction, the only reasonable response is to pick up that rock, hold it, feel its weight, and wonder, what are you still not seeing?